Hello, everyone. Welcome to another section, chapter 11. So, in section 11.1, we look at the introduction of trees, and now 11.2, we look at a few application of trees, right? So, how can we apply tree into a real life application? Okay, so first we look at binary tree. So what is binary tree? So binary tree, we have the definition in section 11.1, right? So binary tree is a full tree with two children at each vertex each, right? So there you go. It is a rooted tree with no vertex have more than two children, right? So each child designated as a right or left child, and each vertex is labeled with a key, right? So we focus on that. So vertices are assigned keys so that the key of a vertex is both larger than the key of all vertices in its left subtree and smaller than the key of all vertices in its right subtree. All right. So that's the vertex. Okay. And the first item in the list will assign as the key of the root. So each vertex is a key, but the first item in the list of the question will designate as the root, and then everything will follow with that. So to add the new item, we first compare the key of the vertex with every vertex already in the tree, starting from the root and moving to the left of the item if it is less than the key of the respective vertex. And if it will become the left child, or moving to the right if the item is bigger than the key of the respective vertex, and this vertex now become a right child, right? So we do a comparison between every single vertices, start with the root, and then we do a pair comparisons on that. So you know, when the item is less than the respective vertex and this vertex have no left child, then this will be as the new left child, right? Similar to the right one, the right side comparisons. All right, so that's how we're gonna build a binary tree. Remember, the left one will be on the left hand side, the larger one will be on the right hand side, and we do comparisons. All right, to show you more clear on that, so let's take a look at the example here, right? So suppose we have we try to build a binary search tree for the following words: banana, peach, apple, pear, coconut, mango, and papaya, using alphabet orders. Okay. Now you might wonder, what does it mean by using alphabet order? Does that mean that we have to start from the first letter in the alphabet? The answer is no. That's when you try to compare. Okay. So what is the root? So according to the tree, it said the first item in the list will be the root. So this guy here will be the root. Okay, so banana will be the root. So you can see the comparisons that we're gonna have. So we're gonna have banana. All right, that will be your root. And then now you compare peach to banana. All right, so that's when you apply alphabet orders, right? So banana and peach. So peach is larger in the alphabet order compared to banana. So therefore, peach will be on the right-hand side of banana. Okay. So the larger item will be on the right-hand side. And next one is apple. So now you have apple versus banana, right? So apple versus banana. So apple A before B, so A before B, so A will be on the left-hand side of banana. So apple here. So notice that banana, apple, and peach now should be the same level, right? Because you compare to the root, and one is bigger than the root, and one is smaller than the root. So they are the first child of the root. So they are on the same level. Okay. Next one we have pear. All right, so pear compared to banana, so pear is bigger than banana. All right, it's just like, you know, when you go through checkpoints, right? So pear versus banana. So P is bigger than B, so P will be the right hand side. So now you can imagine that pear travel, now pear versus peach, right? So now you got pear versus peach. So very important, right? They are the same P, they are the same E, they are the same A, and last one is R and C. So R is bigger than C, so pear will be on the right hand side of peach. So this is pear, okay? One at a time. Make sense? So next one, similarly, coconut. So coconut is bigger than apple. Right? I mean, coconut is bigger than banana. So move on to the next row and then compare to peach. And right, so you compare one at a time. If you pass the first row, you compare to the next row and so on. So coconut is smaller than peach. So coconut will be on the left-hand side of a peach, okay? So this is coconut. Next one is mango. All right, mango is bigger than banana, but mango is smaller than peach. And then mango is bigger than coconut. So mango will be on the right hand side of coconut. And papaya is bigger than banana. Papaya is smaller than peach. And papaya is bigger than coconut. And papaya is bigger than mango. So papaya will be on the right hand side of mango. And that's when you complete, right? So remember, coconut and pear, they have the same parent, which is peach, so they're on the same size. And then mango will be by itself, papaya will be by itself. So that's what's the level, and then how we construct a binary tree using alphabet orders. Okay, makes sense? All right, so we do one at a time, right? Banana will be always the designated root because that's the first item in the list. And peach is bigger than banana, will be on the right-hand side. Apple is smaller than banana, will be on the left-hand side. Pear is bigger than banana on the right-hand side. And then pear, compare letter by letter, is bigger than peach, so it's on the right-hand side. And then coconut is bigger than banana, but smaller than peach, so it's on the left-hand side of peach. And then that's how the list follows. Sounds good? All right, so that's how we build a binary search tree on this. All right. Now, next one is what happens if you try to add a random item onto the existing binary search tree? Yeah, we do the same thing, right? So when you want to insert something, then you want write command. Okay, so I have a root, and then I try to compare that item with a root, and I try to compare the left tail, the right child of that, and then I keep doing the same comparison, and then you can add the new vertex if you needed to. All right, so this is an algorithm that you can try to do to build a binary search tree. All right, so suppose that we want to add the word lemon into the binary search tree in the previous example, okay? So I'm gonna bring back that previous example. So we have banana, and then we have peach here, and then we have coconut. Oh, I mean apple, yes. We have apple here, and then we have pear here. We have coconut here. And then we have, what do we have? We have mango. And then we have papaya. Okay. All right. So, right. Okay. There you go. Banana, apple, peach, coconut, pear, mango, and papaya. And now we're gonna take a look. What happened if you want to add a binary search tree on that, and we try to add lemon on that. So again, lemon. So now you're gonna take lemon compared to banana. So lemon is bigger than banana, and then lemon is bigger than banana, and then lemon is smaller than peach, and lemon is bigger than coconut, but lemon is smaller than mango. So lemon will be add on this side right here. So that when you add lemon, so lemon and papaya will be the same level. Okay. Okay, so that's how you add that. So you do a comparison at the root first. So banana, peach, and then coconut, and then mango, and then lemon. That's where you add lemons. All right, one at a time. All right, so make sense? All right, let's go next one. So sometimes when you have a graph, a tree that's not really a full binary tree, you can always add in unlabeled vertices when it's necessary to make sure that you have a full binary search tree. So here's the example. On the left-hand side, the tree T, it is binary, but then it's not a full binary. Then we can add a few more unlabeled, edges, so that we can have a full binary search tree. Okay, so from T to U, you can see here. Okay, so those are the one that we try to add. Initially, it doesn't have any, right? So just add the one that doesn't have any label yet, right? So that's something we can do. Now, another one is we have is also a binary search tree, but then it have decision tree because it's well providing the outcome of each decision we're going to make. For example, if you look at the mathematics website, we say, okay, I want to do engineering. What math do I need to take? So those are the decisions that's focused on the binary, binary search tree on that, right? Decision tree. So you can see here the example. So if you are less than 30 years of age, then you jump to around, like, are you student? If yes, then you go to the right hand side. If no, you go to the left hand side. And then you bigger than 40 years of age, then you look at the credit rating, whether excellent or fair. All right, so this is a decision tree example. Okay. Now another application here is we have prefix code. So this might be familiar with you guys. 1001, things like that. That's the prefix code. It's a bit string for another letters, right? So by looking at those numbers, you can recognize, okay, what letter do I fill in here and things like that. So we call that prefix code. So yeah, we can use a binary search tree to presenting a prefix code on that. And each of those gonna have a label on the leaf of the tree, and that's how we know which series to look for. So here is the idea is that the left child will be assigned as a 0 always, okay? And then an edge leading to the right child will be assigned a 1. So in this book, we're gonna follow that construction. So on the exam, make sure you follow this idea, right? Left child is a 0 and then right child is a 1. So here is an example, right? So yeah, we have a root and we have E is a 0, right? So go to E, you're gonna go to 0 and things like that. So if you take a look at the idea here, so if you want to travel to 0, the code will be, to E, the code will be with 0. You want to travel to A, the code you need to go through will be 1, 0. And you want to travel to T, the code will be 1, 1, 0, right? So you always start with the root. And the code to N will be 1, 1, 1, 0. And the code to S will be 1, 1, 1, 1, right? So those are the coding using the prefix code to representing each, letters or a series of letters, things like that. So when you see 1111, you know that, oh, the letter is an S, okay? For example, suppose we have this coded, right? 1111011100. And then you look at all the idea here and you can see, okay, so E is equal to 0, A equal to 10, and T equal to 110, and then N is equal to 1110, and then S equal to 1111. So we're going to use those code and to see whether we can decode the message that somebody sent us using just numbers. All right. So there's no way it's going to be the letter E first because there's no 0 starting first. So there's a few possibility here that you can see. So you can have, you can have 11141 together. Okay, suppose we try to decode this. All right. So it have to be S at first because you can look at all of that. You have 1 and 0, 1110, and then but then you see here like you don't see a 3, 1, and a 0, right? So therefore we're gonna go with it. Okay, I'm gonna go with a 4, 1 first. So 1, 2, 3, 4. So that's an S. So next one you can say, well, you can do 1, 0 or 101, but then there's no 101. So it's either 1, 0. So we're gonna go with that 1, 0, which is A, right? Okay, and next one you can see, can I do 1, 1? Well, there's no 1, 1. Can I have 1, 1, 1? Well, there's no 1, 1, 1. That will be 1, 1, 1, and 0. So we're gonna go with that block right there. So that will be an N, and last one is the leftover will be an E. So you decode that to become sand, right? That's the idea. Make sense? Yeah. Okay. So that's what we have. Prefix coding, right? So one application of prefix coding is Huffman coding. So Huffman coding representing using probabilities, input as a sequence, which are the probability of occurrence of the symbol in a string, and produce as outputs a prefix code that encode the string using the fewest possible bits among all possible binary prefix code for this symbol. So this will consider as Huffman coding. So we're gonna have a list of probability, and we need to build a Huffman graph based on this. Now, what is special about Huffman coding is that because every letters have the weight, and the idea is that the larger weight is always on the left hand side. Remember, we go with the opposite. Usually the larger weight is on the right hand side, but the larger weights for Huffman coding will always be on the left hand side, and the lighter weight will be on the right hand side. So however, it still follow the prefix code, which is 0101. Okay, so again, larger weight doesn't mean that it has to be the 1. Larger weight, it is 0 in this case because Huffman said that larger weight will be on the left hand side, but then it still follow the prefix code 0101. Okay, so we don't flip 10 because there's a larger weight on the left hand side. No. Okay, be careful with that. Remember that. Make sure on the exam you do it too. All right. So yeah, so we try to add. First, we need to put them in ascending orders from smallest to largest, and then you combine 2 at a time. The reason we combine 2 at a time is that it is binary code, right? And then you can see until we finish everything else. So first you write everything on the sequence, and then you compare 2 at a time, and you add them together to get a sum, and then you compare with that sum with the next one, and you add them together, and then you keep going until the end of the example. Okay, and that's when you finish the root, right? So here is the example of Huffman coding. So the letter A will have probability of 20%. Letter B will be 10%. Letter C will be 15%. Letter D will be 25%. And letter E will be 30%. All right. So we try to do that. So solution is that first we need to lay down in order of decreasing weight, not the alphabet, but the increasing weight. So yeah, I noticed here B will with pawn 10. So you know, I have pawn 1 here, so this equivalent to the letter B. Next one is C, which is pawn 1 5. And next one is A, which is pawn 20. And next one is D, which is pawn 25. And last one is E, which is 30. All right, so now we're gonna go from left to right, right? So now we're gonna focus on these two first. You're gonna add them. All right, so pawn 1 plus pawn 1 5 give us pawns 2 5. So pawn 1 plus pawn 1 5 give us pawn 2 5. So that would be the new weight. All right, so what does that pawn 2 5 contain? Pawn 2 5 contain to B and C. So which one is bigger? So pawn 1 5 is bigger than pawn 1, so therefore C is on the left. So pawn 2 5 contains C and B. Okay. Now you compare pawn 2 5 to everything else. All right, so now you have a new list. Now the next one is pawn 2. That's still A. And now pawn 2 5 and pawn 2 5 doesn't matter which one you want to combine. So you can have pawn 2 5 here. So this one contains C and B. And then pawn 2 5 where you have D alone. And then pawn 3 where you have just E. And then you gotta do this 2 again. All right. So you got pawn 2 plus pawn 2 5. So that's give you pawn 45. Now pawn 2 5 is larger, so it will be on the right hand side. So A will be here, and this guy were containing C and B. So remember, this guy and A are the same level, yes, because one is pawn 2 5 and one is pawn 2. And then that's how you go to C. Okay, so A, B, C are not on the same level. Pawn 2 5 and pawn 2 are the same level. So now you have pawn 45. Then you compare with this 2 and this 2 to see which one's bigger. All right, does that make sense so far? Well, we do 2 at a time, right? Don't rush, okay? All right, so next. All right, I'm gonna write that again. So we have here is pawn 45, which contain pawn 2 5 and then pawn 2, and then pawn 2 5 contain pawn 1 5 and then pawn 10. And this happened to be the letter C and the letter B. This guy was the letter A. And then we have D, which is, pawn 2 5, and then E, which is pawn 3. So now you can see here when you compare that, this guy will be pawn 45. Yes. So now you have pawn 2 5, which is D, and then pawn 3, which is E, and then pawn 45, which contain those over there, C, B, and A. So now you get the next 2 because that's the next one in the list. So you're gonna plus that. So you get pawn 2 5 plus pawn 3. So give us pawn 55. And what does this pawn 55 contain? Pawn 55 contain pawn 3 and pawn 2 5, which is E and D. Remember, the larger item is on the right hand side. So now you have pawn 45 and pawn 55. So you're gonna compare to that. Pawn 55 is bigger. So next one you want to do is that you're gonna have pawn 55 plus with pawn 45. So that's give you 1. So this one will contain pawn 55 and then pawn 45. Pawn 55 contain E and D. Pawn 45 contain A here, and then this one sub tree of them. So this compare C and B. So there we go. Okay. So it contains 0.25 here, and then 0.2 here, 0.3 here, 0.25 here, and 0.15 here, and then 0.1. So this is what we have. Okay. So now you're gonna write the whole list of that. So here's the all things together. So you're gonna have here as the root, and then you're gonna go here, and go there, then you're gonna go here, and you go there, you go here, you go there, and then you 2 more branches coming out, and that's how you have Huffman coding. So this one E, this one is D, this one is C, this one is B, and this one is A. And this still 0, 1, 0, 1, 0, 1, and then 0, 1. All right, so you go with the list. A will need 1, 1. B will need 1, 0, 1. C will need 1, 0, 0. D will need 0, 1. And then E will need 0, 0. You can see here, starting from the root, you want to go to E, you're going to go 0, and then 0. You want to go to A, you're going to go 1, and then 1. All right, so that's how you follow the branches, right? You can see here, 1, 0, 0 will give you C, 1, 0, 1 will give you B. Okay, so that's what we have Huffman coding. So we do 2 at a time, right? So always start from the ascending orders, and then you go from there. Sound good? And that is the end of 11.2. All right.